Yeah, you can maybe share your screen. And you can take a look at
Yeah,
this.
yeah. Are you able to see my screen now?
Not yet. Yeah, it's coming up. Okay. Yeah, yeah, just a second. Let me try to maximize this.
Yeah. It's going to start at $1. Is my uh, currencies of the vending machine, and once I insert 25 cents, it goes to 25 cents straight, and then it waits there. And then if I insert 25 cents again, next it goes to 50, and then when it goes to 75, it dispenses out. And there's always a return condition if you don't want to if you don't want if you want to cancel the transaction, and if you are at 100, it will dispense out and it will go to 25 state because it has to give you 25 cents in return.
Hmm. Yeah.
And uh, you, and you can always click return to go to the state zero and give you the coins out if you want to cancel the transaction.
Okay.
This is the state diagram that I have, and with the code.
Yeah, just
So
quick
I
question.
have,
What's a D loop there? Within each state, there's a loop that you have shown, right? I think marked by D.
yeah.
What's that?
Until and unless if you have not added much more coins, then it remains in the same state. So if you have added 25 and you have stopped it, then it is stuck to the same state.
Okay.
Yeah.
Okay.
So
Yeah, let's
yeah,
look at
with
the let's
code.
look at the code here.
I guess these are all the parameters that I have taken. The input clock, reset, and the output is dispense out and coin out. So registers, open and state, the next state parameters I have given zero as zero,
And
micro as one, 50.
can can we quickly go back? What's the N and D input?
So the N is the next one and D is the default.
N is
So it
next.
goes,
Okay, I don't
yeah.
understand that. Can you explain what N and D will do for you?
Uh, so so it basically is that um, if you are giving a 25 cents to the vending machine, it should go to the next state from 0 to 25. So I've named that as N.
Oh, okay, okay.
Uh, uh, yeah. So, to begin with, I've given the parameters which are 0, 25, 50, 75, and 1 because we may also exit till 1. So always depending on the next state, default state, and based on the state conditions, if D, if it is if it has increased, then I go to 25, and uh, yeah, and, mm, yeah. So if I add like two coins, it checks out what is the next state. The first state is 25, and the next is 50. So we need 75 cents to dispense out soda. So the dispense at 50 would be zero, and the coin, if you want to return it, then the coin out will be 1. If the case at 75, uh, if reset is not equal to 0, then if it is not asked to return, then the dispense will be 1 and coin out will be 0 because you get a soda because it has reached 75 cents. And if you have reached $1, then the next state would go to 0 because you have asked for a soda and also a return of a coin out, which is 25 cents. And this is the default condition to reset the device to 0. I'm not sure if I'm right. Please cut me out if I've missed something.
Yeah, there are a few places where you can maybe make changes. One is
Okay.
when you talk about the first always block, always at N or D. First of all, N and D is not the right naming convention for ports, right? The naming convention should be 25 cents or whatever, something appropriate, what you can understand.
Okay.
Uh,
Okay.
and that is the only other input you need. See, what is the input? Clock and reset is just the input for your design. But the main, I mean, for
Mm-hmm.
the hardware part of it, but the main design, what is the input? Input,
25
currency
cents.
input is the input, right? The currency is the input. So you can say 25 cents or whatever, some give some appropriate names or send 25, something like that. And
Mm-hmm.
that's the only input you need from the machine perspective. And the
Okay.
outputs, there are two outputs as correctly shown: dispense out, and coin out, or return, whatever you want to call it, coin return or
Mm-hmm.
something like that. So that
Okay.
is fine. Then reg and parameter definition is fine. You can do it the way you want. Always at N or D or state. Uh, your machine will
Can I
state
just give
machine,
25 cents?
right? So your machine will only work with respect to state in the sensitivity list,
Okay.
because that's one always block in which in your case it's shown at the bottom. Even let's talk about the bottom always block first. Always at passage clock, if reset or not of N and not of D. So you should not have that. Always at passage clock. If reset, if fine. If you're checking for reset, if reset state gets 0. So state on reset
Mm.
state goes to 0. Else state is next state.
Okay.
We don't want to check any other input there. All we are really doing is assigning next state to state in that always block.
Mm-hmm.
Then coming back to the first always block, it should be always at state. That's it. The
Okay.
sensitivity list should not be anything else, because the other always block is assigning next state to state.
Okay.
So this always block will always be with respect to state. Now there are few corrections I would like you to do. Is one thing, if you look at it, for 0 state you are defining something. For
Mm-hmm.
75 states you are defining some logic. For $1 state you are defining some logic.
You want me to define it for 25 and 50 as well?
Right. For 25 and 50, there is no logic defined. That's those are two things you can change. And what you can do here is you don't have to check for reset again in this always block. In this case, 75 cent state, where you're again checking for reset, and even $1 state.
Okay.
Why? Because you're already checking for reset in the other always block, and if there is no reset, only then next state will go to state. Otherwise, state will be in zero condition.
Okay. Okay. So if this is declared, then I don't have to write if reset
Reset, you
next
don't
state
have to
is
check
0.
reset. In case you want to check for reset here, the way you should do it is always at state. This always the first always block, line number 6. First of
Yeah.
all, after always block, there should be a begin, because begin and end for the always block, because you have multiple statements there, right? In the always
Okay.
block. In that, you should first check for reset. If reset state remains in 0, next state remains in 0.
Okay.
So next state 0 means in the other always block, next state 0 will again go to state, again it will come back in this always block. If there is a reset, it will stay in 0. So if you look at
It's
the
like
left hand,
multiple
multiple
transactions
reset.
for one,
Yeah.
multiple reset and always.
So you don't really have to check, but if you're going to check in the first always block, if reset, next state is equal to state, next state is equal to zero, end that
Hmm.
thing.
Okay.
Else, else means for reset there is else. If there is no reset, then this case statement will be there in the else part.
Okay.
So either you don't check for reset at all in the first always block, or if you're going to check it, check it. If reset, then next state is equal to zero, and then end that thing. Else,
Okay.
if if there is no reset, then check for the case. Then there should be a case statement with state as
Okay.
a case variable. And as we
Okay.
have written down, there is no logic defined for 25 cents and 50 cents.
Okay. I will
Right.
add that as well.
And the only thing you can check is 75 cents state and $1 state. You're checking for reset. Rather than reset, you should check for 25-cent value because that is the input, right? In this case, N
Yeah.
for because currency is going to define whether the soda will be dispensed or not.
Okay.
See, look at you have to look at it. There are two perspectives. There are two perspectives to this. One is the digital design perspective, where you need clock,
Mm-hmm.
reset, etc. But look at it from a vending machine functional perspective, from an end user
Mm-hmm.
perspective. When an end user now supposedly this will be developed on a FPGA. That FPGA is part of the vending machine. Let's assume that.
Mm-hmm.
So vending some user who doesn't know anything about technology, all they really want is they're going to insert coins. If enough coins are inserted, they will push a button, they will get a soda. As far as they go, that's all it is through the machine. From that perspective, the only input is currency, which is 25 cents multiples. Or in your case, you have assumed that there could be a dollar bill also. If you look at the state diagram.
Okay.
In the state diagram, you say from state 0, you can go directly to 100 state,
Mm-hmm.
right? How can you go from 0
Yeah.
to 100 state in one step? By inserting a dollar bill
Yeah.
directly.
Right.
So that is another input you will have in your case. If you don't want that, remove that path between 0 to 100, direct path.
Oh, okay.
Otherwise, in your case, there will be two inputs. 25 cents is one input and dollar bill is another input.
Dollar is one input. Yeah. I got it.
So you either change the state diagram or you change the design, depending on how you want to make it work.
Mm-hmm.
On zero state should have an arrow showing reset. So it clearly shows that on reset it will go into zero state. That's my ideal state of a FSM.
Okay.
Okay, so that is how your state diagram is, and then you make the necessary changes in your Verilog code. The Verilog design, you are naming it as vending machine.text. Okay,
Yeah.
it should be called vending machine or whatever dot v. Dot v extension is for Verilog.
Okay.
It should not be a text file. It should be a dot v file. V for Verilog.
Okay. Yeah.
Then your Notepad++ that you are using will also show the color coding scheme even more correctly. It's showing right
Okay.
now, but it can even show further better in that case. One
Okay.
more input I would like to give you is I don't know, have you if you've done any programming before, you should indent the code properly, right? So there should be spaces between two lines. Then always
Yeah.
then it should be starting at the correct column number. So always begin same column. Then anything between begin and end of the always block should be one. Anything in between should be one column inside that. So from line number 8 in this case to line number 14, for example, yeah, should be one tab or some one tab inside the whole thing. So that will give you good indentation. It will show you the case
Okay.
statement belongs inside the always block. So those kind of changes you can, those are superficial changes, but you can, since it is a good habit to be formed right now to do the indentation correctly.
Yeah, right.
So,
Yeah.
so those are the changes you can make them, and maybe next time we will see again how it works. Okay.
Yeah, sure.
So, okay, sounds good. Let me just, then I'll share it. Okay, so let me know if you can see the screen.
Yes, I can.
I can.
Yeah, it's visible. So this is where we stopped last time. We looked at memory design. We saw how memory theoretically can be defined from a digital logic perspective. And once we understand the memory definition from a digital logic perspective, how do you convert that to a Verilog model using, in this case, behavioral modeling method? So, any questions on whatever we've seen so far?
No.
No? Okay, so we
No.
continue with the next slide where we talk about pipelines or pipeline design. Pipeline design is exactly what it is called. It's a pipeline based approach. So a chunk of combinational circuit or chunk of combinational logic followed by a flip flop. Again, some combinational logic followed by a flip flop, and some more of those combination circuit and flip flop. What it does is every time a combinational circuits are these are called registered. So we say that the outputs of combinational circuits are registered when there is a flip flop. So uh, basically, the logical paths pipeline designs are useful when you're working with high speed designs in hardware. When you're working with high speed designs, uh, the way it works is, let's say I want to work on 100 megahertz design. Excuse me. Let's say I want to work on a 100 megahertz design. So 100 megahertz is the clock cycle. If you convert it to time, it will be 10 nanoseconds per 100 megahertz. When I say 10 nanoseconds is the time period of 100 megahertz. So when I say my design is supposed to work at 100 megahertz, let's assume there are 100 different logical paths in the design. Different paths means there is various logic defined and there are various paths in the design. Each of the path has to meet that 100 megahertz requirement or 10 nanosecond requirement. So sometimes what happens is, so this combinational circuit, now if let's say I remove this flop. So let's say combinational circuit lot section 1, 2 and 3 followed by flip flop. This is going to be a very long path by the time this is going to get registered. By the time you reach the flip flop, this is the part from input to the flip flop output is considered one path through the combinational circuit in case of static timing analysis or timing analysis. So if you do that, removing the flops in between, it's going to be a very long path. Chances are your design is not going to meet timing. So for high-speed designs, we follow this structure called pipeline structure. There are some combinational circuits it's followed by flip-flops. Again, then this goes to section 2 of combination circuits followed by flip-flop. This is called registering the outputs. So now we are cutting down the path from this point to end of the flip-flop. This is path number 1. From this point to end of the flip-flop is path number 2. From this point, input of the combination circuit to output of the flip-flop becomes path number 3. Now there is a very good chance my all the three paths will meet timing of 10 nanoseconds. Okay, do you understand this concept? Why something or design will be pipelined in the first place?
Yeah.
Yeah.
So, so that is why we would pipeline a design or we will create a structure of pipeline. So this is an example of a pipeline design and how do we do it? How do we implement this is shown below Verilog. So A and B are two inputs. There is an adder. You get a sum output, which is then fed to the D flip flop. Is registered basically. It becomes sum output. C input is directly going to a flip flop. We get D underscore C as the output of that. These two sum and D underscore C values are multiplied. There is a product term. You get a product term called P, which is again registered or passed through a flip flop, and we get the final output. Now, if you want to write Verilog code for that, this is the Verilog code. Now, we are not defining the module and the input-output ports. That is assumed that you understand that module and port definitions can be done. This is a core logic part of it. Wire n underscore sum and p. N underscore sum and p. These are two wires I need. Red sum d underscore c and out. Reg sum because I need to implement a flip flop. So sum d underscore c and out are the three flip flops I'm going to need. I declare a reg for that. Assign n underscore sum equal to a plus b. N underscore sum, this wire is getting, we are using a continuous assign statement. N underscore sum gets a plus b. This adder will be implemented here. Assign p is equal to sum star d underscore c. P is wire gets product of sum and d underscore c. This multiplier will be implemented here. Again using a continuous assign statement outside the always block. So the adder and the multiplier is implemented using continuous assign statement outside the always block. We need the always block to implement the D flip flops. Flip flop 1, 2 and 3. How do I do that? Always at passage clock. So my sequential circuit flip flop and synchronous circuit using clock will be implemented. Begin the always block. Sum gets n sum at passage of clock. Sum gets n sum. This flip flop will be implemented. D underscore C gets C. D underscore C gets C at positive edge of clock. This flip flop will be implemented. Out gets P. Out gets P. This flip flop number 3 will be implemented using this line. So end the always block. So using the always block, we are able to implement flip flop 1, 2 and 3. And using the continuous assign statement, we are able to implement this adder and this product term multiplier. So using and for to implement all this, we need certain wires which are net data type and registers to implement it. So this is a pipeline design, and we would implement Verilog using this method. If you really want to implement, if you want this, okay, hold on 1 second. Let me see if I can get it back a little bit. No, maybe not. Okay. So let me also include the module definition here. So we'll have a complete design with this. We will pipeline ABC out. Verilog is a case sensitive language. So input is a keyword as long as it is small case. Same with output. Okay, for now we'll keep it like this, and later on I'll adjust it for better reading purpose. So now we are defining a module and end module. So we have the inputs and the output. Then we have the local wire and dredge declarations. This is a continuous assign statement outside the always block. This always block will give me the three flip-flops that we talked about, then followed by end module. So this is a complete definition for a pipeline design. So this is how pipeline designs work. And the reason we would pipeline any design is to make it work at higher speed. So we talked about this, that if we don't have this flip flops in between, this whole thing will become, and then there's only a flip flop at the end, then the whole thing will become a single path, which in certain high speed cases won't meet or potentially won't meet timing requirements. So we break it down, we register the outputs, and then we meet timing. So for our high speed designs. Any questions you have regarding this concept or this slide in general?
Yeah.
No.
So please note down this design, this example. This will be if you are going to attend any interviews. It's possible you get asked about pipeline designs or pipeline structures, or you may get asked about how to implement high-speed designs. A pipeline structure is one way to implement high-speed designs.
I'm done.
Okay, done.
I'm
Hello.
done too.
Okay. So, efficient modeling techniques. Just hold on a second. Can I move this? Yeah. Okay. Efficient modeling techniques. So there are certain guidelines. If you follow those guidelines, it will generate good, efficient, reliable, and efficient hardware. See, why are you using Verilog? Verilog is a language, is a hardware description language, and ultimately, whatever you define in Verilog will get converted to hardware, either on FPGA or an ASIC device somewhere. That hardware that gets generated should be reliable and efficient in nature, because that's a good design in that case. And there are certain guidelines. If you follow those guidelines in Verilog, will always there is a very good chance that the hardware generated will be reliable in nature and efficient in nature. So what are those guidelines? You try to separate the combinational and the sequential circuits as much as you can. Ideally speaking, you completely separate them. Separate the structured circuit and random logic. So a structured circuit will have data paths or what we call data path modeling. Then the random logic will be control logic for the design. So The data path logic, if you separate that, so any continuous assigned statements will give you data paths. Always block, using always block, or even sometimes continuous assigned statements also you can generate control logic, but it's mostly using always blocks. So the structure, the data path and control logic, if you separate them completely, it will be better. Then like point number one, wherever possible, you separate the combinational and sequential circuits. Now, where in the earlier example, if you saw the pipeline design, this was the combinational circuit, this was the sequential circuit. We separated it out. It was possible here. Use parenthesis control complex structure. So if in case you are working on multiple operators, let's say you're going to add something, then the result is multiplied by something else, then the final result is subtracted out of something else. So now you are working with three operators. Wherever possible, use parentheses around your operations. So the synthesis to know which operation to perform first, then operation second, and then operation third. So you are in better control of your design in that case. So let's look at the inefficient description. Now how do we change it? Module count is the name. Clock, reset, AND bits, OR bits, XOR bits is my port list. Out of which clock and reset is single bit input ports, AND bits, XOR, OR bit and XOR bits are single bit output ports. Reg AND bits, OR bits, XOR bits, the same name as output because I'm going to assign the values inside the always block. Reg 2 down to 0 count. There is another reg called count, 3 bits. Always at passage clock. This is a synchronous design. Begin the always block. If reset, count gets 0. Count is resetted. Else count gets count plus 1. So I'm incrementing count by 1 if reset is not activated. And bit. So this is where the if else if statement ends here. Since there is only single line after if, we don't begin and end. We don't need a begin and end. Same with else. There is only single line after else. There is no requirement for begin and end. Then AND bits is equal to AND count. So this is a unary reduction operator as we call it, if you remember from the operator section. So AND bits equal to AND count means it's a unary reduction operator. How does it work? Count is 3 bits, 2 down to 0. So the second bit here will be ANDed with the same register first bit. The result will then get ANDed with 0 bit. And finally the whole thing will generate a single bit result, which will then be assigned to AND bits. OR bits is equal to unary reduction operator OR with the count. So in this case, instead of AND, it will OR within the same bits, 3-bit count register. Second bit of count will be logically OR with first bit of count. That result will then logically be OR with bit number 0 of count register. Finally, we get 1-bit value as a result, which will then get assigned to all bits. XOR bits is equal to logical XORing. This cap sign is the XOR sign. Unary reduction XOR operator in count. Count bit number 2 will be XORed with bit number 1 of count. The result will be again XORed with bit number 0 of count register, which will then generate a single bit result, which will then get assigned to XOR bits. End the always block end module. So here we are saying this is an inefficient description as far as the guidelines go. Can you, before we see efficient description, can you try to guess or try to using the guidelines that we saw, why is this called an inefficient description? And possibly point out how we can make it efficient. Do you want to see the guidelines slide again?
Yes. One second, please.
Okay, so can we go back to the other slide?
Yeah. Can we use non-blocking in this?
Yeah, non-blocking is one thing, but that's not the efficient part. Yeah, surely we can convert it to non-blocking.
And is it like can we declare all of the sequential circuits separately, like AND, OR, and XOR, instead of having it only in one always block, and we declare it differently?
So which part is sequential and how can we declare it differently? Can you be more specific?
I'm not sure, but like all the gates that we have over here,
Okay,
so
which gates?
AND, OR, and XOR,
Okay,
for that, instead of having working at one clock cycle, can we have like different clock cycle to have it work in more efficient ways?
okay. So how do I do that? Any ideas? So you're saying I have this always at passage clock begin to this, then end here, end this always block here. Then have another always block at passage clock begin and have these three lines and then end the always block. Is that it?
Yeah, I'm not sure, but
Yeah, that's okay. One guess, right? You're trying to guess and trying to maybe provide input. Is that one way to do that? Is there any other thing that you would consider?
can I use it as case, like case statements? If this is the case, then AND. If this is the case, then OR. And if this is the case, then XOR, XOR.
How will you use a case statement? Case statement is normally used, as we saw earlier, in case of state machines, right? State machines are
Yeah.
required. Machine in the sense we follow a logical path from one step to another step. That is typically when you would need, if in case you have something like that, then you would need something like a state machine. You go from one state to other state, from that state to third state, but we don't have any such thing here, right?
Yeah.
So okay, now let's take on one step back. So what is the sequential part and what is the combinational part? Or everything is sequential or everything is combination? Logic was. That's a key to understanding this. That's why I'm trying to stress on this. No? Okay, I'll show you the next slide. You explain to me how this works. Now, this slide talks about efficient description following the guidelines. How do you read this slide? So unfortunately, in PowerPoint, I cannot show two slides side by side. But basically, the earlier slide you saw, this is the updated version of the slide. And we say that this is efficient description. Why do we call it efficient description? Now it's in front of you. Can you read and tell me why it is called efficient here and why it was called inefficient in the earlier slide?
So in the efficient one, first you're checking for the count, and based on the count, then you are executing the next always block. In the non-efficient one, I guess you have everything in the based on one clock cycle.
Right, that's a very long description. But how would you describe it from a digital logic perspective? You're correct. The count is done separately. Based on count, something else, some other calculations are done. That's just a very long part of it, right? So, but from a digital logic perspective or from a guideline perspective, why is this efficient and why was the other one inefficient? Ultimately, it's the same logic. We are not changing the logic per se. If you look at the earlier slide, the logic is same. Only thing we are dividing the logic into always blocks. So how do we say this or why do we say this? It's an efficient description. Okay, I'll explain. Going back a couple of slides back, this is the guidelines that we saw. Separate the combinational and the sequential circuit wherever possible is guideline number one. Separate the structured circuit where data paths and control logic will be separated wherever possible. This is guideline number two, and the parenthesis part is okay. We try to control the multiple operators. Now in this case, this section here is going to generate flip-flops for me on count register. Always at passage clock. If reset count is 0, else count is count plus 1. So this is going to generate a counter. Counter is made up of flip-flops. So this section is made up of sequential circuit of flip-flops. AND bits, OR bit, XOR bit is basically AND gates. Unary reduction AND operator means it's successive ANDing of bits or successive ANDing of successive ORing of bits or successive XORing of bits. So ANDing, ORing or XORing is part of combinational circuits. AND gate, OR gate, XOR gate. Basic gates are part of combinational circuits. So this section is part of combinational logic. This section is part of sequential logic. Sequential and combinational combined into one always block. No, as per guideline number one. So inefficient. Go to next slide. Efficient. Why? Sequential circuit of counter, combinational circuit of AND gate, OR gate, XOR gate, separated into two always block. Separate combination and sequential circuit, which follows my guideline for good design purpose. That's why this is efficient. Why? Because we have separated the sequential circuit, we have separated the combinational circuit in two always blocks. Okay, do you agree to this? Hello?
Yes.
Yeah.
Yes.
So that's why this is called efficient description and the other one is called inefficient description. So having said that though, when you work on big designs, we eventually work on very big and complex designs. This is not always possible. Okay, separating completely the combinational circuit and separating completely the sequential circuit. Wherever you can, you should do it, but it may not be possible everywhere, depending on the logic that you're trying to build. But wherever you can, you should separate out the combinational circuit and the sequential circuit, due to which it will generate efficient hardware for you. Efficient in the sense it will take optimum number of gates or optimum number of components in the back-end part of the design when the synthesis does its work, converting Verilog to gate level matrix. That is when the design efficiency comes in. Okay, so you note down this couple of slides. This one is the guideline and the other two examples. So and then we can go forward. Any questions, by the way, on how it is called efficient and non-efficient?
No.
Okay.
Yeah. I'm done.
Done with the slide.
Yeah.
Yeah.
Next slide. And the count assignment should be non-blocking in this case. So we make that change also.
I'm done.
Done. Next slide.
I need a second. I'm done.
Okay, next slide.
I'm done.
Done. Niru.
I'm done. Yeah.
Lare. Okay, so what's the time? Yeah, we'll cover this next time. Okay. So this slide
Okay.
onwards we'll cover next time. Any questions so far?
Sure. No.
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 So next class will be Monday, same time. So if possible, complete the vending machine example. We will look at that, and we'll also look at the other sections of this training in that case. Okay.
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 Okay. Have a
Sounds
good
good.
weekend. Yeah, bye-bye.
Thank you.
You too.